Hello students, welcome to KlassPM. In today's class we are going to discuss about vibrational spectroscopy. The first spectroscopy we have discussed, that electronic spectroscopy. So the second one is vibrational spectroscopy, which is part of again molecular spectroscopy. So what is this vibrational spectroscopy? Okay, so whenever there is a change in the vibrational motion of a molecule, okay, when there is a change in the vibrational motion of a molecule, it is absorbed in the region of IR, infrared region. Okay, it is absorbed in the infrared region. That's why this spectra is also called IR spectroscopy. Vibrational spectroscopy we can also called as IR spectroscopy, because if there is any change in the vibration of a molecule, that change can be absorbed in the region of IR region, so that it is also called IR spectroscopy. Now let's come to how which molecules will be exhibit this visible spectroscopy. Which molecules can be absorbed in the IR region and which molecules cannot be absorbed in the IR region. That means which are IR active, which are IR inactive. There is a condition, you can call it as a selection rule also. So that condition, all the molecules which follows this condition are called IR active molecules. For those molecules only we can see the vibrational or IR spectroscopy, and that condition which do not follow, those molecules cannot be observed for IR or visible vibrational spectroscopy. So what is that condition? The condition is that if there is a vibration in a molecule, if there is a vibration in molecule, it should change its dipole momentum. The condition is that if there is any vibration in a molecule or a compound, change its dipole momentum. Okay, so there is a two kind of changes in the dipole momentum. For example, we know that dipole momentum is a vector quantity, so it has a direction and it has a magnitude also. Both it have, it's a vector quantity. Now how the dipole momentum will change? Dipole momentum can be changed in two ways, either in the change in the magnitude or change in the direction. So I have taken a molecule AB. It's a polar molecule. So we know that polar molecule, what happens? The high electronegative atom will attract the electron pair towards it, so that it gets partial negative charge and other atom will get partial positive charge. Okay, this is a polar molecule. So in the polar molecule, now let's take it, it is rotating in this direction. It is making rotations. So now what happens here? This is positive charge and this is the positive, you can say that positive pole, this is a negative pole. Now both are rotating. What happens here in this? Magnitude is not changing. So let's say that the direction is in this direction. Now here what's happening? This molecule is rotating on its own axis. Now what happens? Here negative pole, negative field, and here positive. When it is rotating like this, here positive, here negative. So there is a periodic change in the electric field, or you can say the charge. There is a periodic change which is changing the direction. So here dipole momentum is changing because direction of dipole momentum is changing. Now if it is like this, direction is in this direction. Now due to it 360 degrees it is rotated. Then it's again came, again the direction is same. It is 180 degrees rotated. Now 180 degrees rotated. Now what happens? B comes here and A comes here. So that now the dipole momentum is in this direction. Okay, see here negative charge, partial negative charge, here partial positive charge, dipole momentum is in this direction. 180 degrees rotated in this angle. So what happens? Now B came here, A came here, and the dipole momentum direction has been changed. Now this kind of change is called rotational change, rotational vibration. This we will discuss later. Rotational. Another way, This is not our topic. This is, we'll study in the rotational spectroscopy. Now our topic is vibrational spectroscopy. My intention is to make you understand dipole momentum can be changed in two ways. One is, if direction changes also dipole momentum changes, if magnitude changes also dipole momentum changes. So here what happened? Due to change in the direction, here due to change in the direction, that you have to remember. Dipole momentum changed due to change in direction. So this is the way here dipole momentum has been changed, and we will discuss this one in the rotational spectroscopy. Okay, look at here. I have taken a molecule AB. So when comparing to A, B has high electronegativity, so it attracts the shared pair of electrons towards itself. So it will get the partial negative charge, it will get the partial positive charge. This is the condition. Now what happened? These molecules are started vibrations. So whenever there is a vibration, two types of vibration is possible, that is coupled vibration, decoupled vibration. Coupled vibration means the relative position of two atoms is changing. So this is A, this is B, both are vibrating. This is called coupled vibration. So both atoms are relatively changing their positions. So this is coupled vibration. Decoupled vibration means one atom stays in that place only, another atom only will changing its momentum. So its position. So this is called decoupled vibration. So here whether it can be decoupled vibration or coupled vibration, whatever. So what happening? It started vibration. So while vibrating, what happens? Expansion, contraction, expansion, contraction. That is why it's happening. So how do you measure the magnitude of dipole momentum? Magnitude of dipole momentum mu bar is equal to the distance between, the separation distance between the two atoms, that is, I will take it as R. The separation distance between two atoms, that is R, into the charge on atom, the charge, whatever charge is present on it, that is Q. This is the way we will find. Now here the magnitude is not changing. The same electron which is going towards B because of high electronegativity of B. Here the same number of electrons, same charge transfer, but the change in what? Here the distance between these two atoms has been changing, increasing, again decreasing. So here the magnitude mu bar is changing because change in distance between two atoms. That's why here when there is a vibration, there is a change in the dipole momentum. So the compounds which will change their dipole momentum during the vibration, only those molecules or compounds will exhibit vibrational spectroscopy or infrared spectroscopy. Understood this one clearly? So it is only the selection rule also you can call it. The dipole momentum of a molecule is changed when it started vibrating. Okay, when its constituting atoms started vibrating with respect to each other. So if that case, dipole momentum is changed. How the dipole momentum is changed? Here the dipole momentum is changed due to the change in internuclear distance. Okay, the distance between nuclei of two atoms is increasing, expansion and the contraction. So here the dipole momentum has been changed due to increase and decrease of the internuclear distance, okay, due to change in the R. That's why here the dipole momentum has been changed. Now we will discuss much thoroughly about the IR spectroscopy. Here we need to remember one more point, that is there is no change in the direction. Direction is in the same direction, A to B. The direction that did not change, only the magnitude has been changed. Okay, dipole momentum can be changed in two ways. One is change in the direction, change in the magnitude. In the earlier example, that is when rotated the molecule, what happened? There the direction changed, magnitude does not change. But here magnitude is changed due to change in the internuclear distance between the two atoms which are vibrating with respect to each other. Next, but the direction does not change. That's what we have to remember here. So then how it is observed in the IR spectroscopy, because here there is a vibration, the continuous oscillation. Vibration is nothing but oscillations are occurring. So this oscillation is having a particular frequency. These oscillations will have a particular frequency. Then we are sending a electromagnetic radiation to this. If this electromagnetic radiation frequency and this oscillations frequency matches, this electromagnetic radiation frequency and this frequency both matches, then this absorption can be seen in the IR spectroscopy. Okay, because IR spectroscopy frequency can be matched with these vibrational frequencies, so that this is absorbed in the region of IR, so that it is called IR spectroscopy. Now we will take one example. We will try to understand how these vibrations will start. Okay, let's take a polar molecule like hydrogen chloride is a polar molecule. So I am taking here, we know that the chlorine size is larger than hydrogen. Now hydrogen is here, chlorine is here. So here we need to understand one important phenomena regarding chemical bonding. Let's try to understand this first. This is a nucleus of atom A, and in the atom A there are 2 electrons are present. Next, another atom is there, B. It is a B atom nucleus, and it is having some 6 electrons in its outermost shell. Look, for example, we will take the 2 atoms, that is atom A and atom B. Okay, and this is positively charged nucleus, and these are the electrons, those dots are the electrons. Now between these 2 atoms, 2 kind of forces will exist. What kind of forces those are? This nucleus will attract these electrons. This nucleus will attract these electrons. Okay, nucleus of A will attract the electrons of B. At the same time, nucleus of B will also attract the electrons of A. At the same time, so there is a attraction force between the nuclei of 2 atoms and electrons of 2 atoms. So nucleus of B atom is attracting the electron. Both are oppositely charged. This is positive charge, the electrons are negative charge. So that there is attraction force between the nucleus of atom B and electrons of A. At the same time, there is attraction of nucleus of atom A and electrons of atom B. This is the attraction force. Now these electrons of A and electrons of B both are negatively charged. We know that the same charges will repel each other. So there is a repulsion force. At the same time, nucleus of A and the nucleus of B both are positively charged. That's why both will repel. So between these 2 atoms, 2 kind of forces exist. One is attraction force, other one is repulsion force. Okay, if these 2 atoms will form a bond or do not form a bond, it depends on the strength of these 2 forces. If attraction force is greater than repulsion force, if attraction force is greater than repulsion force, there is a chance for the bond formation. If repulsion force is greater than attraction force, so no bond formation. If repulsion force is greater than attraction force, no chance for the bond formation. And there is a attraction, if attraction force is greater than repulsion force, then it is a chance for the bond formation. Okay, so what happens? So between them 2 kind of force are acting here. So what happens? They will come to sufficiently closer range of distance together. So both will come to a certain place and they will stop coming closer together, because if they come more closer, what happens? Repulsion force increases. If they go away from each other, attraction force increases, so that they will again brought to some place. So they will come and stop at particular distance. That distance is called equilibrium distance. Now the distance, because both are stable at this distance, the internuclear distance whatever is here, at this distance which we are calling R equilibrium, that is equilibrium distance. At R equilibrium distance, both atoms are stable. If they come much more closer than this distance, the repulsion force increases, and if they go away from each other, attraction force increases, so that again they will brought together. Okay, when they are coming, repulsion force is increasing, so that they will pushed away, and if they are going away, what happening? Attraction force is increasing, so that they will come again. So this kind of, with this understanding, with this knowledge of attraction and the repulsion forces and equilibrium distance, now we'll try to understand how these vibrations causes. Okay, look at here. Now I have taken HCl molecule and the chlorine and the hydrogen, and both are at a particular equilibrium distance. Let's take this distance, whatever distance is here, that is, this is a or equilibrium distance. At a particular distance, hydrogen came and stopped. So let's assume here chlorine is relatively large and hydrogen is relatively small. So we'll take it as chlorine is static, it does not make any change in its relative position. Only hydrogen will make vibration, which will come closer to the chlorine and it's go away from the chlorine. So only decoupled vibrations are possible in the case of hydrogen and hydrochloric acid, HCl. Okay, let's assume that since the chlorine size is large, it will be static. Only hydrogen relatively small, it will come closer. Like when you play the yo-yo, but you will hold the yo-yo in your hand, just you will push, give some force to it. What happens? It will go and come back, go and come back. Okay, like that. Chlorine will be in its position and hydrogen will make vibrations like this. Okay. Now what we do is, so let's imagine one real life example. Take a rubber band and stretch it. What happens? Stretch it to some extent and leave it. With how much distance you stretch it, with that much force it will come closer to the, again it will come and throw. Same thing you can do with the spring which you find in your pen, or sometimes in vehicles also you will find the spring like this. Okay, so that spring you will push it, not pulling, you push it, don't stretch it, put a constant close it. So what happens when you push it will undergo some tension, so immediately when you remove your hand it will again expands. Okay, that you might have observed in real life. Take a spring which is in the pen, then it push it closer like this, push it closer. What happens? It comes under a tension, so that whenever you remove your finger, again it will expand, and expand it whenever we remove our hand, again it will come closer. So these two things we might have observed, which are led to the vibration of this one. So what I have done is, chlorine molecule here, now I pushed it some distance here, up to here I pushed it. So what happens? Since I put it here, push it here, when I remove my force, it again get back to some distance. Okay, there is a vibration. When I pushed it here from this place to, I pushed it little, so it expands a little. So we'll go with the same distance. I pushed it much more closer, so that it is made a large vibration again. Again I pushed it much more closer. Due to repulsion force, it is pushed back. So what we have found just now, what I have given example of spring, when you push the spring closer, what happens? Due to tension, it will go back. Same kind of vibration. This is the equilibrium position. Now when I pushed it little closer to the chlorine, towards the chlorine, due to increase in the repulsion, the chlorine pushed the hydrogen away from it, so that it goes away. Again it will come much more closer. Again it push back. Again it will come closer. Again it push back. Now here the one question you should get in doubt. When it pushed away, it should come and stop at where it started. Why it is coming closer? Why it is coming? A good question. See, for example, a stronger person pushed me away. So when I am going, again holding my shirt, it dragged me towards him. So that what happens? I should go and stop where from my original position, but I won't stop there, because since I am a molecule, I am an atom, due to inertia, I blindly goes little towards the inside. Okay, due to inertia, it won't stop in its original position, it will go much more closer to that. Say for example, this is a condition. So what happens? I try to push it here. So due to repulsion, it pushed this atom to other way. So it should come and stop here only, but it won't stop here. It will come little closer to it because of inertia. So because of inertia, it will go towards here, so that again there is an increase in the much more repel, so it push much more away. So again attraction force increases, again it will come closer, much more closer, again go away. So this kind of vibration will go on, so that if I connect the dotted lines, I can find a hyperbola. See, this kind of. So this is my vibration range. Here vibration increased, here vibration also increased. Why vibrations are increasing here? Because these vibration, how much distance it's going. See, here we need to apply Hooke's law. What Hooke's law says? Now what I am doing here, when I am pushing hydrogen towards the chlorine, in the opposite direction, I am pushing hydrogen towards chlorine. So in the opposite direction, one force is produced, that is called restoring force. Restoring force which will keep it in its original position. Try to keep it in original position. There is in the opposite direction, one force is produced. That force is absolutely directly proportional to the distance of expansion or contraction. See, from here to here I pushed. So base depends on this distance. See, this distance is smaller. X distance it's produced. X distance I pushed inside. So that what happened? Force F is produced, which pushed it away from its original position. Now here my X value increased. See, this distance greater than this distance, so my X value increases, so that the force also again increases, so that it push much more away. So here again the X distance increases, I push it much more closer, so again X distance is increased, so that what happened? The force is produced, the restoring force intensity also increases, magnitude also increases, so that it push much more away from the chlorine. So that here what we have to understand is the restoring force which is produced in the opposite direction is directly proportional to the distance. So since this restoring force is produced in the opposite direction, we can keep it minus. So I can say that minus F inverse to the distance, let's take it X. So minus F is equal to K is the force constant. So I will send the minus that side, Kx. So here F is the restoring force which is produced when there is a contraction or expansion from its relative position. Okay. So and here the K is the force constant, the X is the distance between two atoms. Okay. If there is a change, everything will change. Okay. Okay. A molecule start vibrating. Okay, these vibrations will continuously. So then how it is observed in the IR spectroscopy? Now it is making some periodic oscillations, like from this position, this position, this position, periodic oscillations. So it is having a certain frequency. If this frequency of oscillations is matches with the sending IR spectroscopy wavelength, the frequency. So both the frequencies, whenever this matches, it absorbs the IR region electromagnetic radiation. So this is the way it can be identified in the IR region. Okay. So we can summarize what we have learned so far. So if a molecule want to make a vibration in it should change its dipole momentum either by changing the direction or by changing the magnitude. In the vibrational spectroscopy, there is a change in the molecule when there is a vibration in its dipole momentum due to internuclear distance change in the atoms. Okay, because when vibrating, the magnitude will remain same, but internuclear distance will changes. So because of that, there is a change in the vibrational, and this can be observed in the IR region. That's why it is also called IR spectroscopy. In the next class, we will continue our vibrational spectroscopy.